US of A is going back to the moon, and this time we're staying. NASA's Artemis missions are putting astronauts back on the lunar surface within the next decade. But here's the catch. The moon has a problem. It's covered in razor-sharp, static-charged dust that sticks to everything. It clogs seals, blinds sensors, it tears through equipment, and we're planning missions that will last months, not days. Now, NASA has existing dust shields, but they're rigid, bulky, not easily adaptable, and space doesn't care how expensive your hardware is. Tech researchers have engineered something revolutionary. A flexible dust shield that can actively repel lunar dust while bending and flexing. That's where we come in. We're Team Dustless Daves, and we're building a first-of-its-kind testing apparatus that measures shield performance while it bends. Our device delivers the data researchers need to push this technology toward NASA standards, and maybe even onto the lunar surface itself.
All right, now let's get into how we defined our problems so that we could fully accomplish the goal of our stakeholders. In order to make this film commercially viable, our testing apparatus has to adhere to an existing mechanical bending test standard. We chose this specific standard, IEC 62899-2025, because, similar to our EDS film, it tests the flexibility of a printed circuit on top of a flexible film. This means the testing apparatus follows a specific structure. It will have a fixed plate on top with a moving plate on the bottom that repeatedly bends the printed layer according to certain critical parameters such as bending radius, linear motion distance, cycle time, and number of cycles. Row 3 of this table illustrates another hidden design challenge to preserve the film's integrity. The gap must be greater than 10 millimeters while the chamber evacuates. This means for small radius tests, the device must be able to remotely adjust to the desired radius. Additionally, the vacuum chamber limits our size, materials, and sources of motion. Therefore, our device must adjust for the listed parameters and actuate to the correct plate distance, all using one source of motion. So, how does our final design accomplish this? It uses existing structural connections to connect to the vacuum chamber at the top, and at the bottom, it features one rotational feed-through that actuates our falling fixed plate mechanism to set the bending radius, and a Scotch yoke mechanism to convert that rotational motion into linear reciprocating motion to accomplish both tasks. The plate dropping mechanism is simple. It takes advantage of the first turn of the motion to actuate a latch, which drops the fixed plate from greater than 10 millimeters to a preset gap as defined by customizable stop rods. That same wheel drives our reciprocating motion and in steady state. First, the shaft rotates the pin featured on the wheel, and in that horizontal slot, the yoke converts it to linear reciprocating motion. We take advantage of vacuum-compatible rails and bearings to allow the yoke and the carriage of the moving plate to move in a linear cycle. We use different pin positions on the wheel that directly correlate the pin's radius from the center of the wheel to the linear motion, allowing us to adjust linear distance with pin placement and cycle time with motor speed. We were successful in translating this design concept into a viable prototype that, through testing, demonstrates that we are confident in translating this design into vacuum functionality. As shown, the device confidently fits within the vacuum chamber. To prioritize and engineer for human factors in this design, assembly time was reduced by reducing parts to around 35 minutes. Additionally, the parts needing sonication were minimized to the 2 stop rods that need to be replaced between tests. In this functional demonstration, the falling plate actuation comes first. Notice the pin at the bottom of the wheel that pushes the bottom latch out of the way so the plate can begin to fall. Next, rotational motion is converted into linear reciprocating motion through the Scotch yoke mechanism, and the rods on either side of the mechanism hold the constant bending radius flat. Additionally, the 2 threaded connections on each plate successfully secure the film without penetrating the critical bending radius area. Despite this, a slight mismatch in film size and bending radius led the film to slightly sag during testing. This emphasizes the need for specific film sizes for every permutation of testing factors when creating a testing procedure in the future. Engineering analysis on our final design revealed a few critical implications for functionality in vacuum environment. The tolerance of the flatness between the 2 plates is the main driver of our ability to achieve the small bending radiuses in the standard. As shown through the tolerance stack-up, it was determined that the Georgia Tech machine shop could achieve a plus or minus 1 millimeter tolerance between the plates, whereas precise manufacturing can achieve a plus or minus 0.5 tolerance. Given this, the minimum achievable bending radius is 1 millimeter. Given the maximum of 20 millimeters, we still believe that this bending radius achievement is significant enough to adhere to the standard. Another critical risk is advanced wear due to metal-on-metal contact in a vacuum. This analysis illustrates an extreme worst-case scenarios where the bearings, the most heavily loaded piece of the apparatus, are constantly sliding instead of rolling against the rail. This shows worst-case linear wear of up to 2.5 millimeters, which would be detrimental to conducting tests at small bending radii. Therefore, any pieces with metal-to-metal dynamic contact were replaced such that one of them is vacuum-compatible ceramic. Overall, our design successfully accomplished its critical functions, and with further testing, we are confident that a machine version with correct materials can accomplish this test for the Clever team. Using this, Dustless Daves can help engineers' hard work return to the moon permanently. Thanks for listening.